In the late 19th century, electromagnetic phenomena had been expressed as charges, currents, and magnets propagating fields that then acted on other charges and currents in accordance with the Lorentz force law. However, this notion was not always the most convenient for tackling complex problems, so physicists came up with various ways to combat this.
Physicists use the divergenceless property of magnetic fields in order to express them as the curl of a vector potential A. In this manner, potentials were assumed to be purely mathematical constructs and were not uniquely defined by their physical effects. However, Aharonov and Bohm argued that an electrically charged particle could be affected by a magnetic potential even if it was confined to a region of zero electric and magnetic field. The most common case of the Aharonov-Bohm effect occurs when a charged particle passing around the long solenoid experiences a phase shift due to the enclosed magnetic field, even though the magnetic field is negligible in the space where the particle passes through. This setup is similar to that of the inside of a CRT television set, where the image on the screen generated by the electron beam can be shifted with the effects of a current-passing solenoid. In our experiment, the non-zero vector potential comes from a current-carrying solenoid. The relationship between the vector potential and the magnetic flux inside the solenoid can be seen on screen. Aharonov and Bohm predicted a phase shift based on the formula you see on screen. But since the expected quantum phase shifts are too small, the flux value inside the solenoid needs to be kept as high as possible. In our experiment, my teammates and I intended to deflect the electron beam coming from the cathode ray tube and observe a shift of the image projected on the television screen. With the help of some very kind industrial workers, we wound tightly a sufficiently long solenoid so that the magnetic field on its outside parameters would be negligible. We then opened up a CRT television set to reveal the cathode ray tube and hooked up the solenoid to a voltage source. We then brought the solenoid closer and then farther to the cathode ray tube in hopes of seeing an image shift on the screen. However, in our initial run, we observed nothing of the kind. We assumed that our current values were not enough to create a sufficient flux, so we hooked up the system to two voltage sources to up the current. However, even with the increased current value, we were still not able to see any shift on the image on the screen. With the continual unsatisfactory results of our experimental trials, we assumed that the voltage sources we used were just not sufficient enough to get the current values that we needed. However, personal communication with an upperclassman at our university led us to a different understanding. The Aharonov-Bohm effect relies on a closed loop, where mainly then can the magnetic field be written in terms of the potential vector, which causes it to also relate to the flux. This relation can be seen on the equations on screen. However, the restrictive nature of the cathode ray tube prevents the electron beam from going around the solenoid to create a phase shift, as can be seen by this figure. This effect, thus, can only be realized with the utilization of a non-restrictive electron emitter, where the electrons would have the path to move around the solenoid freely. However, even with such revisions, the quantum mechanical nature of this effect may deem the results of this experiment on the macroscopic level to be imperceptibly minuscule.